I will begin with a word of prayer. Heavenly Father, we thank you for this day. I thank you for this class, and I just ask you to be with us today, help us to glorify you in what we do, and understand a little bit more about orthogonal complements and adjoints and all these things. Lord, in your name I pray, Lord Jesus. Amen. Okay, so we just got to the definition of the perp, right? And so this was the definition. If S is non-empty and S is a subset of V, this is a inner product space. All right. Then S perp is defined to be X in V such that X inner product Y is equal to 0 for all Y in S. All right. In other words, the perp to S is the set of all vectors in the space which are perpendicular to the vectors in S. All right. So this is also called the orthogonal complement of S. And it turns out that this is in fact a subspace, right? So I think I had threatened to make that homework, but I think after the dust settles I failed. So I guess it's up to me to prove it. Let's do that. So theorem, S perp is a subspace of V. All right, again, I'm assuming S is not empty, right? Okay. So if, so here's the proof. 0 is an element of V, and 0 with anything, right, is 0. So therefore, 0 is an element of the perp, right? Which is apparently then non-empty. So we start to prove it's a subspace by checking it's non-empty. What's our next move? Addition. Yeah. Well, I'm gonna go for a twofer. So yeah, let's try for both. So let's let x1 and x2 be an S perp and C a scalar, right? Then if we calculate C x1 plus x2 with y, let y be an S, all right? Let y be an S. Then by properties of the inner product, additivity and linearity in the first slot, right? This is cx1y plus x2 with y by, like axioms A and B, I think, of the inner product. But what are those? That's C times 0 plus 0 equals 0. Thus, cx1 plus x2 is perpendicular to every vector in S. Therefore, cx1 plus x2 is an element of S perp. And that is a subspace of V by subspace test, right? All right. So there's that. So it is a subspace. And it's a subspace whether or not I mean, there's a, I didn't see this in the book, but it's actually kind of important to know about, just in terms of situational awareness. And like, here's another result. I'm just calling it a proposition. If W is equal to the span of S, then W perp is equal to S perp. So in particular, an application of this is, if beta is basis for W, then we can calculate W perp by finding beta perp. All right. Now, so let me show you an example of that. So like example 1, for instance, if I'm looking at, W is, I don't know, let's say A in 2 by 2 such that, A transpose is equal to minus A. So that's a subspace, right? You can check. That's a subspace of R2 by 2, right? This is in fact equal to the span of 0, -1, 1, 0, if you work it out. And so if I want, I can just calculate the perp of the singleton, and I would be looking for, B in R2 by 2 such that what? The inner product of B and this matrix is 0. You can almost see why this is going to work, right? If I looked at the span of that matrix, it doesn't really change the calculation any, does it? Right? See what I'm saying? Like a typical element of W is just a constant multiple of this matrix, right? So if I, instead of checking perpendicularity with this one fixed matrix, I check perpendicularity with scalar multiples of this matrix, it's the same criteria for B. That's essentially what this proposition gives you. All right? I'm not going to prove it. I'll let you guys prove that one. So what does this work out to? This is the Frobenius inner product, right? So this gives us B11 times 0 plus B12 times -1 plus B21 times 1 plus B22 times 0 if you just work it out. Which apparently tells me what? It tells me that B12 is equal to B21, right? And I get no condition whatsoever on B11 and B22, right? Those are free. So what is this? Well, apparently it's the span of matrices of the, well, I can just write it out. It's the span of this. Or if you like, I could have also written this collectively as the condition B transpose equals to B, right? So the perp to the antisymmetric matrices with respect to the Frobenius norm is the symmetric matrices, right? This is the symmetric matrices. All right. Okay, so I added that example here. This example not in the book. All right, so next up we have a theorem. If I can squeeze it in somewhere. I think I'll put it over here. Rats. I gotta get the juice. Yowzers. Should we spread the rumor that we had a bonus quiz today? Is it wrong? No.
You could just give us a bonus quiz with a really simple problem that will take very little time, a minute long problem.
Yeah, no, I don't think so. All right, so let W be a subspace of V. You guys are funny. Where V is finite dimensional. Inner product space. All right. And oh no, we're V. My bad. V is an inner product space. I shouldn't say finite dimensional on V. And W is finite dimensional. All right, W is finite dimensional. Let Y be an element of V. Then there exist unique vectors U in W and Z in W perp such that Y is equal to U plus Z. Furthermore, if V1, V2, Vk is orthonormal basis for W, all right, then U is simply equal to the sum I equals 1 to k of the inner product of Y with Vi. All right. So that's the theorem. So, all right. The interesting thing is V could be infinite dimensional and we can still do this, all right? Because we only really need the finite basis for W to make this all work together, all right? So essentially the theorem already kind of tells you how you're going to construct the U. So we let Y be an element of V. We construct U like this, okay? So the proof goes like this. Let W equal to the span of V1 through Vk, where V1, well, let me just write it this way, where the inner product of Vi with Vj is Kronecker delta Ij, right? So that's a quick way of me telling you that the basis is what? Orthogonal, but more than that. Orthonormal. We can do this because we can Gram-Schmidt followed by normalize, right? So we can always find an orthonormal basis for any subspace, and we do that, all right? Now that I've done that, let Y be an element of V, and construct U equals to the sum I equals 1 to k of the inner product of Y with Vi. So I don't know how well you guys remember Calc 3 or not, but this should remind you of the fact that we can take a vector and we can break it down into like a dot product with the unit vectors. This is reminiscent in Calc 3, we do the thing like, vector v is what? It's like v dot x hat times x hat plus v dot y hat plus v dot z hat if we're talking 3 dimensions, If we have a orthonormal basis, like say maybe you used IJK in your course, whatever. You guys had my course though, some of you, but not you. IJK. Remember IJK? My IJK are x hat, y hat, z hat. Those are unit vectors in the direction of x, y, z. But that's what this formula is based off of, right? The inner product is a generalization of the dot product, and that's just selecting components with respect to an orthonormal basis. That's where this is coming from, the idea of it. All right. Now, once you have that, how would you find z? What do we want z? How do you construct u like that? That's fine. We got that vector. How about z? What do we make z? It's right. It's so stupid, right? And z equals, what did you tell me? Subtract u from y? Yeah, y minus u, as we're used right above, right? Then, of course, y is equal to u plus z, right? It seems almost too stupid to be right. Now that alone is not the interesting part, right? You could play this stupid game in many other contexts, right? You can call something a name and play this game of defining the difference of the other thing, and oh look, the sum of the two things is the other thing, yay! But what makes this interesting, of course, is that u actually is, that z actually is in the perp to w, right? We need to check that. Is that actually the case? So how do we calculate that? We're going to look at z with vj. All right? Z with vj is going to be y minus the sum I equals 1 to k of y with vi, comma vj. So I just put in the definition of z. Now I'll use the properties of the inner product. All right. So that's equal to the inner product of y with vj. And I'm going to use the additivity. I'm going to pull that sum out. I've got to minus the sum I equals 1 to k of, and I'm going to pull that number out. Y with vi, right? What's left? Oh, the inner product of vi with vj. Aha. But we know what that is. We are working with an orthonormal basis, right? So this is the Kronecker delta ij, which is the natural enemy of the finite sum. That sum collapses to just the jth term. Lo and behold, yvj minus yvj, also known as 0. Therefore, z is an element of beta perp. I'm calling the basis beta for the sake of a current discussion, right? Beta. But my proposition says that beta perp is equal to W perp, right? Let me put it into words. Maybe we should prove the proposition. Why does the proposition make sense? Why is it that if it's perpendicular to everything in the basis, it's perpendicular to everything in the subspace? How do we build vectors in the subspace? They're spans of the basis, right?
Yeah, you just add together the basis vectors, which means if those all go to 0, the whole thing goes to 0.
That's right. So because of the additivity of the inner product, if we can break up the sum over the basis into a linear combination of the basis elements against the z. And since the the inner products of Z with all the basis elements are 0, the linear combination is just sum of zeros, which again gives us 0. To be careful, we could prove the proposition I wrote. Yeah.
Is it a somewhat vague notation to say beta perp as opposed to span of beta perp? Or is that...
No, I literally mean beta perp. I mean the set of vectors which are perpendicular to the basis.
Okay. Individual.
Yeah. Yeah, that's what that proposition was saying. It's saying something non-trivial. It's saying that if you find the set of vectors which is perpendicular to the basis, which is a finite set of vectors, that same set you obtain if you find the set of vectors which are perpendicular to the infinity of vectors which form W itself. It's enough to be perpendicular to the basis. The perpendicularity with the rest of the spans of the basis automatically follows. That's the proposition. The claim of the proposition I didn't prove today. Which I should have put in the homework, but I already got pressured into making this homework somewhat prematurely. Thanks, Daniel. Yeah. So. All right, let's go on. Now, technically I should also check uniqueness, because it says there's unique vectors U and in W. How do I know that how do I have uniqueness, right? Well, I'm going to let you read the book on that. That's not. I'm going to go on here because otherwise I'm in trouble with time. I know it. The reason there is something to think about uniqueness-wise is I could have chose a different basis, right? If I chose a different basis for W, it seems like the U constructed in principle could be different. But in practice, that concern is actually, unjustified. Oh, fine, I'll just do the proof. All right, so we need uniqueness. Let y equals to U plus Z and y equal to U prime plus Z prime, where we're supposing that we're building the U prime with a basis beta prime, all right? And here we have, of course, U. U is in W. Z is in W perp. And over here, U prime is in W. Z prime is in W perp, all right? So if that's the situation, what happens? We have y minus 0, right, is y minus y, which is also equal to U plus Z minus U prime plus Z prime, right? But that says that 0 is equal to U minus U prime plus Z minus Z prime. All right. Or if you like, U minus U prime is equal to, minus, well, you could do Z prime minus Z, whatever. So if I call this vector, we give it a name, Bob. What can you tell me about Bob? Where is it? I'll start. Bob's an element of W. And Bob's an element of W perp. Why is that? Because this gives me that, right? And U prime are in W. Their difference is in W. So what does this mean about Bob? What about Bob? It's a very good movie, by the way. Bob's an element of the intersection of W and W perp. All right, very good.
That intersection is 0.
Why?
Or, well, the set containing 0.
But why is that the set containing 0? Did I already prove that? That's my question, really.
This vector can't be perfectly conjugate, so that's 0.
Ah. So, lemma. Let's make a lemma. W, and now I'm almost certainly doing part of your homework, but it's okay. Lemma, this is equal to 0, all right? So, pick x in there. What do you have about that x? If x is an element of W intersect W perp, what do we got? That implies that, you know,
It's in W and it's in W perp.
right, so that means that x with x is equal to 0, right? Which by the axiom, or, I mean, I don't know if it's an axiom or if it's a derived consequence, I can't remember, but that does imply x equals to 0, right? And it's also clear that 0 with x, right, is equal to 0 for all x in, you know, for all x in W. And of course 0 is, therefore 0 is in W perp, right? But of course 0 is also in W because W is a subspace. So I have 0 is a subset of, the singleton containing 0 is a subset of the intersection, and the intersection also contains the singleton 0, right? In other words, these calculations prove the lemma, right? Consequently, the Bob is 0, but Bob being 0 is tantamount to U equals to U prime, and Z equal to Z prime, which is uniqueness of the decomposition, right? So that's kind of interesting. There's something deep calculational we're saying here, because how many different bases can you choose for a subspace? Infinitely many different sub-bases, right? So if I think about this, how this gels for like a specific example, you know, if I'm in 3 dimensions and I've got some kind of, you know, funny, you know, subspace, maybe it's dropping down here, here's x, and I'll let y go like that. All right, great, whatever. Z. If I was to take one basis here, you know, say what was my notation? V. So I had I had V1 and I had V2, right? And if I had another basis, say V bar 1, V bar 2, you know, I'm trying. And I was to, you know, take a vector in 3 dimensions, right? If I was to take a vector in 3 dimensions and project it. So in the notation of the theorem, this is y. Okay? So like y projects maybe down to here. I'm just, for the sake of getting away from, I find it bothers me. I'll make up here. So in here, you know, there's a specific vector u, right? And this vector here, I think we've called z, right? That u, I would call the projection. Let me call this plane W. The projection onto W of y. I can either write it as, you know, y dot v1 v1 plus y dot v2 v2, or I can write it y dot v1 bar v bar 1 plus y dot v bar 2 v bar 2. And those have to be equal because it's unique, independent of my choice of basis for the subspace. This proof does this not just in 3 dimensions, but in any finite dimensional subspace, possibly of an infinite dimensional space. All right? And so we have a special name for the U that appears in this theorem. We call it the projection. So by definition, now that the theorem has been stated and proved, we can reasonably define this, right, to be projection onto W of Y. Projection onto W of Y. And if you study this, it's fairly clear that the projection onto W is a mapping from what? It's a mapping from V to W, right? And it's a linear map, right? The linearity is manifest from the formula, because if I replaced Y with a linear combination, I have linearity of the first slot paired with the linearity of the formula. It's easy to prove that this is in fact a linear transformation. So there is a projection. All right. Now we can say more. I'm working on getting a full class behind my schedule. We're well on our way. So here's the corollary. The corollary, if W is a subspace of V, all right, and W is finite dimensional, and Y is an element of V, all right, has Y equals to U plus Z, as we were discussing, right, where U is an element of W and Z is in W perp, all right, then U, which I just defined to be the projection, right, onto W of Y, is the unique vector. We already know that. Just emphasizing it. It's the unique vector in W. Here's its role, which is closest to Y. In the sense, the norm of Y minus X is greater than or equal to the norm of Y minus U. This is for any X in W. And equality is attained only if X is equal to U. All right. It's the only vector that has that length. Right? A picture of this, sort of abstractly, is as follows. So here's my W. All right. And so let me draw the origin on there, and let me draw the U and the Z. Get it all there. So this is my origin. All right. So here's the U, and I guess I should have drawn this one first. Y. All right. And I guess I'll make this Z. I'm going to move my other vector a bit for the sake of artistry. There we go. So these are perpendicular. So you notice that, let me draw some arrows on these vectors just to help us see things better. This goes like that. I can think of I'm drawing u and z as if they're tip to tail, you know. We can do that. So z is equal to what? Y minus u, right? All right. So the claim is, I'm not sure it really helps to put the x in the picture, but let me put the x in the picture nonetheless. So x is some other point where? Oh man, am I out of black markers? I think all my blacks are all kind of dead. I guess I'll have to settle for this thing over here. So the claim is if I put x anywhere, anywhere else, like maybe here, right? Then the distance from here to there, right? That distance would be the norm of y minus x, right? And the claim is that that distance is larger than the distance from u to y. Here's the proof. So we look at the norm of y minus x squared, and we trade that for the norm of u plus z minus x squared. All right. If you forgot, the norm of a vector, right, is what? It is equal to the square root of the inner product of v with v, right? We like to look at norm squared because then we don't have square roots, exactly. So like, squares are great. So we do that. That's just nothing more but what? Y is u plus z. Okay? Now, notice that u and x are both where? Where are they? They're both in w. And as such, they're perpendicular to z by construction, right? So we're looking at the length of u minus x plus z squared. You can prove this is a good exercise for you to work out. It should have been on your homework, but again, I was hurried into making mission 5, and as such, I've forgotten to put this very basic and simple problem on your mission 5. My apologies. By the way, it's technically due 5 days from now, but I'm going to make it due not instead of Monday. I think it's due Monday, but I'm going to move it back to Wednesday just for the sake of you guys having enough time to come ask me questions Monday about whatever you get stuck on. And I'll give you guys 3 skips. I think 6 skips is a little bit too much. So three skips on this one. And please do them in order, and like when you skip something, just write skip there so I know. Otherwise, when they get out of order and stuff, it gets like a little bit much for me to figure out the grading. But anyway, since u minus x is perpendicular to z, there's a Pythagorean theorem that you can prove. The length of the sum of 2 orthogonal vectors is the sum of the length squared. It's not hard to work. It's like a pretty easy thing to work out. It makes a great homework problem. My apologies that it's not in your homework already. All right? So then what? Well, then it's just kind of like, duh. So this is greater than or equal to what? Exactly. Which is what? Right. So that implies, of course, that the norm of
Y minus.
Oh,
U, not Y minus X.
yeah. I was about to get really confused. Okay, so y minus x is greater than or equal to the norm of y minus u because we're talking about positive, non-negative quantities, so we can take the square root of the square and we don't get in any kind of trouble, right? So there you go. And the fact that equality is attained, when you put equals there is pretty obvious. I guess it. And let's see here. If I had equality for a different vector, what would it tell me? You know, if I had norm of y minus x squared equals to the norm of y minus u squared, what would that tell me?
Well, y minus u squared is just the norm of, the norm of y minus u squared is just the norm of z squared.
Yeah, well, anyway. Oh, why do they leave that dreadful thing up here? Ugh. So in the interest of saying a little bit more today, I'm going to move along here and not fuss about the, I'm trying to think. Obviously, equality is attained if x is equal to u, right? That's just, I guess the only meaningful question is, what if x was not equal to u and you attained equality? Why would that be a contradiction? It's like, what if you had x prime not equal to x and y minus x is equal to the norm of y minus x prime. And this, of course, x prime is an element of where? And I probably need to square it. So of course we can go down the thing we just did before, right? This is going to be equal to what? Norm of u minus x squared plus norm of z squared. And this is also equal to what? Norm of u minus x prime squared, I suppose, right? Is that fair? Or not? I don't think it is either. I don't know, let me stop this. This is going nowhere. Let me do the sensible thing I should have done like 2 minutes ago and say, well, look at the book for the uniqueness. Okay, so let me just stick with that. There's a little bit more I want to cover today here. So, all right. So, where was I? Let me erase the evidence. All right. So finally, we have a theorem that just kind of gathers some results together here. If we have S is an orthonormal set, say V1 through Vk, all right, orthonormal subset of inner product space V, all right? Then there's three results here. A, S can be extended. This is the dimension of V is equal to n. That's kind of important here. Okay, otherwise what I'm about to write would be like, huh? So n-dimensional space. That's the situation we're in here. S can be extended to an orthonormal basis for V, all right? And B, if W is equal to the span of S, then W perp is simply going to be the span of the part you extended. So like past K, so K plus 1 out to N. See what I'm saying? The perp is formed by the span of all of the vectors that you adjoined to the basis to get past W. All right? And so C, for any subspace W of V, we have the dimension of V equals to the dimension of W plus the dimension of W perp. So the proof is on page 349 of the textbook, which is probably what I should have cited 5 minutes ago for that proof. I'm sorry I got stuck on that, but it's not, whatever I'm stuck on, it's nothing much, I don't believe. What does this tell us about W and W perp? What kind of subspaces are they? What did we prove today? Yeah, we proved that W intersect W perp is 0, right? And that right there proves that the sum of them is what? It's everything, right? So you put those two things together, and you have that V is the direct sum decomposition of W and W perp. Right? Remember in the discussion of independent subspaces, we had 5 different characterizations, right? And one of those was the fact that there's a unique decomposition of any vector into a sum of vectors in each of the subspaces, right? So that means if I pick X in V, right? In V, in V, right? Then there exists unique, let's call it like, you know, X1 in W and X2 in W perp, right? Such that what?
X is X1 plus X2.
Right. And how would you calculate X1 and X2 if you wanted to? We have formulas. X1 would be the sum, I equals 1 to K of the inner product of X with VI, VI. X2 would be the sum, I equals K plus 1 to N of X with VI, VI. Because that's the basis for W perp, and that's the basis for W. And we can pick off the part of the vector which lies in W or W perp respectively by taking the generalized dot product of the vector with the basis. This is simply the generalization of the concept of projection that we talk about in Calculus 3 to like an arbitrary k-dimensional subspace of an inner product space. And this stuff still works if we're talking about complex inner product spaces. It's very, very nice, I think. So the next section is on the adjoint of a linear operator. So I'll just tell you this, like the adjoint of a linear operator, just to give you a preview, what we're going to do next time is we're going to introduce this new thing called T star. All right. Now we've introduced a star before for a matrix. I don't think we did the operator yet. I hope we didn't, because here's how here's how we're going to end up defining it. If you have T, a linear transformation on V, then we're going to show next time that there exists unique T star, also a linear transformation on V, for which the inner product of T of X with Y is equal to X times the T star of Y. This T star is called the adjoint of T. It just so happens, if we calculate the matrix of the adjoint of T with respect to a orthonormal basis, we're going to find that the matrix of the adjoint is simply the conjugate transpose of the matrix of the original transformation. So the star notation is coherent. All right? But before we even get there, we do something much more interesting, which is we'll discuss the musical morphism. The musical morphism concerns an isomorphism of the vector space and its dual in the presence of an inner product. This is not in the textbook, which is kind of bothersome to me, but that's okay. I'm going to inject it here because I think it's cool. And so we have natural isomorphisms between the vector space and its dual, and between the dual and the vector space using the inner product and like the inverse matrix of the inner product. Anyway, I'm not sure I'm going to say all of that next class, but I'm going to think about it. What I need to do is figure out how much, this may be hidden in the later part of the chapter. I've read it before, but it's been a few months, and I need to, anyway. I am now a solid day behind, but I pushed the homework back a day, so yay.